So here's the new design. The front end of the in-amp has gain of 20, just like before. The back end of the in-amp has gain of 1, which keeps the output from getting railed by a DC offset. This op-amp here is the integrator, which finds the DC offset at the output and then subtracts it off. And there's another amplifier on the output of the in-amp that has a gain of 20, which makes up for the fact that I can't have any gain in the back end. And this variable resistor here is the attenuator that makes the signal smaller as it gets fed to the integrator, which makes it track out DC offset more slowly. The speed at which the integrator integrates, called the time constant, is decided by the size of this capacitor and this resistor right here. But some of the resistance of the attenuator shows up in series with this resistor, which means that along with changing the amplitude of the signal reaching the integrator, it's also going to change the time constant a little bit. But since the resistance of the attenuator is about 1/10 of the resistance in the integrator, that effect should be pretty small, and I should be able to safely ignore it. So another thing about this design that I like more than Jason's is that there's nothing fancy going on in the in-amp part of the circuit. It's just the classic in-amp design there at the front end. This means that if I got an in-amp chip like the 8620, I could just drop it into my design and not have to redesign my DC offset tracking. I'm not going to take the old circuit apart and put this one together just yet. There's still one more thing I have to do first. I want to make sure I'm right about Jason's circuit lowering the gain. So as a control here, I'm going to record with Jason Wen's circuit, and then I'm going to change the circuit to the new DC offset tracker and make sure that it has twice the gain. And now here's the new circuit. At least I hope I have it put together right. So let's see what this looks like. The amplitude looks the same, but there's much less noise. I'm going to have to take another look at this, see what's going on. And I also want to test my DC offset tracking knob. So here I have the knob set to track out as fast as it possibly can. When I press on these electrodes here, it tracks out to about 0 pretty quickly. And then I can turn this to about halfway, which should track out about as fast as Jason's circuit. Looks like it tracks out a bit more slowly maybe. Let's slow it down a little bit more. So now it still does settle down to roughly 0, or about 0.2 I think is where it likes to settle. But it definitely does track out slower when I turn this knob more. If I turn this knob all the way, it should basically stop tracking altogether. Yep. So now the attenuator is set all the way in one direction so that no signal actually gets through to the integrator. Turn this back just a little bit and it should start tracking out. There it goes. Alright, so the tracking speed knob works. So to find out what's going on with the gain. So I think I figured out what's going on with the gain. Turns out I made yet another dumb mistake. I was treating these two resistors here as an adder that was adding these two signals together and then presenting the sum to this integrator. But after doing some more math, a lot more math than I should have done for this, I figured out that that's not what's happening. I'll make it a bit more neat on another page here. So the input to our circuit has two signals coming in. There's some common mode voltage, we'll call that VCM, which is present on both of the inputs. And then one of these inputs also has the signal on it, so we'll call that plus VD. We'll call it plus VDIF for the difference in voltage between these two. One of these signals gets inverted by that inverting adder. So then the signal at this point is negative V common mode. Then the signal hits those two resistors. And the output from there is fed to the integrator. So if we use the voltage divider rule and superposition, we can see that the voltage here is going to be 1/2 VCM plus VDIF, which is the component from the top signal here, minus 1/2 V common mode, which is from this bottom signal over here. Now this plus 1/2 common mode voltage and this minus 1/2 common mode voltage cancel out, and we're left with 1/2 of the differential voltage. So these two resistors do sort of act as an adder that add these two signals together and get rid of the common mode and show the differential signal, but they also act as an attenuator, so it's actually something like this, where it adds the two signals together and then divides it by 2. So we're only seeing half of the differential voltage, which includes both the signal and the DC offset that we're trying to track out. And this signal went to Jason's non-inverting integrator, which integrated the signal and also just presented whatever was at its input directly to its output. So if we ignore the integral part of it and just look at the part that reduces the gain and plug that back into our A over 1 plus AB as B, we end up with 1 over 1 plus 1 half, which means we have a gain of 2/3 instead of 1/2 going through this DC offset tracker. So this explains why my circuit wasn't giving twice as much gain as the previous circuit. So here are the two recordings side by side with the same scale. The recording on the top is from the old circuit, which was Jason's circuit, and the one on the bottom is from my new circuit. Now that I've got the math right, I'm not expecting twice the gain of the old circuit, but I am expecting a little bit more gain, and it doesn't look like that's the case. They look like they have the same amplitude. I also don't know why it has that much less noise in the old circuit. That might have more to do with just the way it's put together. So there's still a couple things going on here that I don't quite understand completely, but overall this does look better, and I still have a few other good reasons to stick with this design instead. And now I want to make sure that the DC offset tracker is not filtering any of my heartbeat signal. So right now I have the speed set about halfway. You can see when I push on this electrode, you can see about how fast it tracks out on the multimeter. So now I'll turn this knob a little bit farther in the slow direction. This slows down the DC offset tracking and pushes the corner frequency of that filter down to lower frequencies. Actually, it's a little bit too far, so it's not tracking out at all. And there we go. Now it's tracking. It's tracking nice and slowly. You can see it takes a while for it to settle back down to 0. And the signal here doesn't look any better than it was before, so it probably wasn't being filtered all that much when I had it set to about halfway, which is here. Now I'm going to turn the knob all the way in the other direction, so it tracks out the DC offset as fast as possible. So you can see it's tracking out quite a bit faster. This pushes the corner frequency up higher, so if anything is going to filter out the signal, it's going to be this. But it still looks just about the same as it did before, which means that I could probably change the resistor or the capacitor and lower them a bit and push the corner frequency up even higher and still not have any filtering of the signal. So I'm going to try that next. So I'm going to get rid of this big ugly electrolytic capacitor, which I never really like using in the first place, and I'm going to replace it with this 0.1 microfarad ceramic capacitor. Since it's 0.1 microfarads instead of 1 microfarad, this should track out about 10 times as fast. And I can always lower the corner frequency with that little knob there in case this is too fast, but this should let me explore a wider range of corner frequencies. Right now I have the knob set about halfway, and I don't see too much difference in the signal than I did before. Let's track out even faster now. Let's turn this all the way up. So I still don't see that much difference in the signal. So you can see even when I'm tracking pretty quickly, there's not much change in the signal amplitude. Yeah, it doesn't look like I'm losing much by putting in a smaller cap. Now I know that at some point, if I keep increasing the tracking speed, it should eventually start filtering out the signal, but I haven't seen it start filtering the signal yet, so just to make sure I'm not crazy, I'm going to make that capacitor even smaller and make sure it actually does track out the signal eventually. These capacitors are labeled in picofarads, with the first 2 digits being part of the value and the last digit being the number of zeros that you tack on to the end. The capacitor that I had in there was the capacitor on the left, labeled 104. The capacitor on the right, labeled 102, is the one that I'm putting in there next. So since it has a 2 instead of a 4 on it, that means you tack on 2 fewer zeros onto the end. So this capacitor is 100 times smaller than the other one, which means it should track out 100 times faster. If this doesn't filter out the signal, then I've got some serious problems. And there we go, no heartbeat signal at all. So the tracking definitely is working. If I have it track fast enough, it will filter out the signal. So there you have it. I can actually track out the DC offset a lot faster than I thought I could originally without filtering out the heartbeat signal. And I think this also means that I can finally call the DC offset problem solved. In the next video, I should be trying to get rid of this noise.